Okay, then welcome back to effective field theory. Last week we did a lot of exercises, and in the week before in our lecture we began with discussing what effective field theories actually are and how they work and how they can be constructed. In short, effective field theories provide for us low energy approximation of some fundamental or a full theory which works at higher energy scale. And the effective field theory provides approximations as Taylor expansions in a small ratio of small energies and masses divided by heavy masses of some heavy particles, which can be integrated out and which do not appear in the effective flow energy theory. In the lecture and in the exercises, we did actually 4 types of calculations, and today I want to summarize what we did so far and draw some important general lessons from our exercises which will be valid for the rest of the semester. Let us begin with 2 lessons from the exercise and also from the lecture. Lesson 1. On the actual existence of effective field theories and how they can be constructed. So, first of all, we have seen in our examples that effective field theories exist. This is the first non-trivial statement, obviously, and we know they exist because we have explicitly constructed them, and we have constructed them in 2 different ways. What are the 2 ways we have used to construct effective field theories? The first way was to calculate Feynman diagrams in the full theory with propagators of hard particles, and then to expand the Feynman diagrams and match them to Feynman diagrams of an effective field theory Lagrangian. Basically, you can do an ansatz for an effective field theory Lagrangian and adjust the terms in the Lagrangian until the effective field theory Feynman diagrams provide a correct approximation to the diagrams of the full theory, and we have worked out explicitly how that can be done, and by observation it works, and therefore the effective field theory exists. There was, however, a second way, which sounds a little bit more general and also provides a reason why the first step works, namely by using equations of motion. By using equations of motion, we can integrate out, as it is the jargon, the heavy particles. And in our cases, this integration works by using the equations of motion of the heavy fields in the full theory, and by plugging in the solution to the classical equation of motion for the heavy field into the Lagrangian. Then the heavy field doesn't exist anymore. It has been replaced by some functional of the light field, and in this way we obtain a Lagrangian which just depends on the light field. And we have seen explicitly in several cases that the 2 procedures end up with the same result, and therefore we know that we have 2 ways to construct effective field theories. Let me stress from the outset that the first way, matching Feynman diagrams, always works, and the second is specific to our 3-level discussion, and we will see the reason why that is. So that is the first lesson. Effective field theories exist and can be constructed in 2 different ways. The second lesson is about the ambiguity in the effective field theories, because we have also seen, and again in 2 different ways, that the Lagrangian of the effective field theory has some redundancy, and that corresponds to an ambiguity. For describing physical observables. And this has again been checked in two ways. Namely, the first way we have observed this ambiguity was by explicitly computing observables using different versions of the effective field theory and obtaining the same result. So, explicit computation of observables and obtaining the same result. And we have done this in two different exercises. In numbers, it was exercise number 2 and also exercise number 4, which is a generalization of exercise number 2. And we have only sketched the solution of this exercise number 2, but there this involves a very elaborate computation of observables, which involve such a redundancy. The second way how to see this ambiguity is to apply field redefinitions or field transformations onto L, onto the Lagrangian. And if we know or use the statement that field transformations are unphysical and therefore cannot change the physical content of the theory, it is clear that by applying a field transformation we go from one Lagrangian to another one which looks different but describes the same physics. And again, we have done this in two ways in exercise number 2 with a very simple and concretely given field transformation, and in exercise number 4 with a generalization. Okay, so these are the 4 different types of calculations that we did, twice with 2 equal results, and therefore we have already learned many very important details about effective field theories. And now I want to expand a little bit on that. First of all, let me give you a more detailed summary of the first type of lesson. We have already done the computation of matching Feynman diagrams for one example, and let me sketch a little bit more general case. And later on, we will then give the proof why this equation of motion method actually works, and this will then, of course, also establish in general why effective field theories exist. Second, I also want to expand a little bit on exercise number 4, which we have only sketched in the exercise class, but let me give you a few more details on the solution. So, next section, let me give you a detailed summary of the construction of effective field theories, which works in 2 ways. So, and I will go back to the example of our section 1.1 of the lecture, and this was similar to exercise on exercise sheet number 2 and exercise number 3. But let's concretely work with our full theory of the lecture, which is this one. Let's write it down. So a normal kinetic and mass term for a light field, a normal kinetic and mass term for a heavy field, a potential which we don't specify any more detailed for the light field only, and interactions involving the heavy field, 1L 2H's, 2L 1H and 3H's. And we have explicitly worked out the Feynman rules for the theory and computed some Feynman diagrams. And let me now sketch and summarize what has happened. So first we have computed processes such as 2L scattering going into 2Ls. So we have done that in our section 1.1, and it involved Feynman diagrams which look, for example, like this, where 2 light and 2 light in the initial and final state connected by a heavy line, and then we can do a Taylor expansion of the propagator of the heavy line and express it in terms of an EFT Feynman rule. But then we have went on, and in the exercise we have considered a process with 5 L's. So that was exercise. Okay, there are different types of Feynman diagrams. One Feynman diagram looked like this. So here 2 heavy lines in intermediate states, 2 L's in the initial state and 3 L's in the final state. And there are many examples of further Feynman diagrams. And one could also calculate processes with 6 L's and so on. For 6 L's it could look, for example, like this. 2 L's in the initial state. Then using the triple vertex with 3 heavy particles and 4 particles in the final state, and so on. So we can compute all these Feynman diagrams, and for each one we can do a Taylor expansion in 1 over the heavy mass scale. And then we obtain the following as a Taylor expansion in pi square over capital M square. This is completely described by an effective field theory. L effective is the same kinetic term and the same mass term for the light field. Then this light original potential, and then additional terms which are now different from the second line in the full theory. So now there come interactions involving only the light fields but not the heavy field. And so after some calculation it looks like this: plus lambda 2 divided by capital M square times 3 over 4 factorial L to the 4th power plus 1 over 8 L square minus D'Alembert divided by capital M square acting on L square, and plus some other terms, and let me write just one term that we have found, minus with an unknown prefactor lambda 2 square times lambda 1 divided by M to the 4th power times L to the 5th. So this is what we found, and with some work we can work out many additional terms, and we can work out all the exact prefactors of the terms in the Lagrangian by requiring that the Feynman rules from here reproduce the Feynman diagrams over there. Now, this is the first way how we can construct effective field theories, which we have applied several times. And let me now summarize the second way, namely using equations of motion. So use the equation of motion for the heavy field H. And so we have already the last time worked out how the equation of motion looks like, so let me copy it. D'Alembert H plus capital M square H is equal to minus lambda 1 LH minus lambda 2 over 2 L square minus lambda 3 over 2 times H square. And in this equation of motion, we now have to say that all the energies are small, and the only, so every term is of dimension 3, and the biggest term is M squared times H. So therefore this is dominant. And on the other hand, here on the right-hand side, there is one single term which does not depend on capital H. And so we can iteratively solve the equation of motion as a Taylor expansion in 1 over m squared. So I just solve for this term here and divide by capital M squared, then I get H is equal to 1 over m squared times the following. And let me start with the H independent term, so minus lambda 2 over 2 capital small l square, then plus all the other terms, so minus D'Alembert H minus lambda 1 LH minus lambda 3 over 2 H square. And then, since we see that capital H is suppressed as 1 over capital M square, it is small by construction. And therefore, the procedure is to plug in the same solution for the equation of motion once again into all the H's which appear here on the right-hand side. And then we get terms which are of the order 1 over m to the 4th, 1 over m to the 6th, and so on. So here we would iterate the same equation. And in this way, we obtain a Taylor expansion in 1 over capital M square on the right-hand side. At any given order in 1 over m square, only L appears and not H anymore. Then in this procedure, we would plug the solution here into the original Lagrangian. We plug it into the full theory, and concretely, if we do it, we obtain the following in this particular case. So H is replaced by the solution H of the equation of motion. We get 1 over 2 dl squared, the kinetic term, minus the mass term, minus the original potential. And then we get one term plus lambda 2 squared divided by 8 capital M square times L to the 4th minus lambda 2 square lambda 1 divided by 4 m to the 4th L to the 5th minus lambda 3 lambda 2 cube over 12 times 8 m to the 6th L to the 6th minus lambda 2 square divided by 8 m to the 4 L square D'Alembert L square plus and so on. And let me just explain where a few of those terms come from. For example, let us look at the first term that I wrote, the L to the 4 term. Where does it come from? It comes from two origins. If we take the solution here, H at lowest non-vanishing order, H is just given by lambda 2 over 2 L squared divided by capital M square. So let's just take this simple solution for capital H, and then we plug in the solution here, here and here, in both places. In both places, if we plug in that solution, we get a term of the order lambda 2 square. We get exactly such a term, lambda 2 square divided by capital M square, and the prefactor coming from here is minus 1 over 4 or 1 over 8, and here the prefactor from here is 1 over 4, and in combination it gives plus 1 over 8 prefactor. So just as an example, this comes from the m square over 2 h square minus lambda 2 over 2 L square h terms. And similarly, all the other terms arise if you plug in the same solution into all the other terms in the Lagrangian. So, and the important observation that we have made is that the result is the same. The Lagrangian that we have written down here, obtained from the equation of motion, is the same as the Lagrangian we obtained here from matching Feynman diagrams. That is the big important observation. Okay, so this is the lesson 1. We can construct effective field theories in 2 different ways with twice the same result. Any questions to this? Yep. Where? Sorry, where are you looking at? Oh, okay, maybe a misprint. In the lecture we did that, so you can check your notes. And looking at the diagram, of course, it must be lambda 2 square. So I would imagine that last time when we did the actual calculation, we also did it correctly. Any other questions? Okay, so that is the first lesson. Let us then discuss the second lesson on the ambiguity. Okay, let us discuss some details on the ambiguities in effective field theories. And we use as a concrete example the exercise number 4 from the second exercise sheet. We sketched kind of the solution and the procedure in the exercise class already. But let me now summarize in a little bit more detail what needs to be done. But the summary is really meant in conjunction with the notes that I provided you on the Selma page. So please work through the notes later on, comparing with the summary that I provide here. I will give you the main items that you need to think about and also the essential solutions of intermediate steps, and of course the lessons that we can learn from it. So that is an effective field theory for a light field small l with discrete symmetry. L goes to plus or minus L. That simply means we have only even powers of L in the Lagrangian. And the exercise illustrates 3 items. The first one is we need to construct the most general versus the simplest effective field theory Lagrangian up to dimension 6 operators. So the first task of the exercise is particularly to construct the most general Lagrangian that is at all possible and then contrast it to the simplest Lagrangian. The second is then to compute observables. Simply compute all relevant observables in the most general case and of course also in the simplest case, which is a specialization. Once you have computed the observables, you observe redundancies. Redundancies mean that the observables do not depend on all parameters separately, but only very specific combinations of parameters actually play a role in the prediction of observables. That is a redundancy. And the third point is to eliminate the redundancies. by field transformations without changing physics. So the logic here is that we put in here the knowledge that field transformations cannot change physics. We know that to begin with. Then we apply certain field transformations and we observe that in this way we recover exactly the same redundancies that we have observed before in the explicit computations. So we get a consistent analysis of the redundant quantities in our theory. So we have two ways to analyze the redundancies, and the second way in particular is then the technical way to eliminate the redundancies by applying field. If you start out with a general Lagrangian, you apply field transformations and go to the simpler but equivalent Lagrangian, where you know from the beginning that the observables will come out the same, but you do not need to go through the computation of the observables in the general case, because that is of course excessively complicated. And the point of the exercise is to really go through this excessively complicated computation of observables in the fully general case with all these unnecessary parameters in the Lagrangian, and see that despite all the unnecessary complexities, you get the same result. And as a byproduct, this complicated calculation teaches you some basic quantum field theory, namely it gives illustration of the LSE reduction for the S matrix and related quantities. But let's go through it step by step. The first point, let us discuss a little bit the general operator basis. How do you get the most general Lagrangian? So let me define a reference Lagrangian, which is the simplest Lagrangian for this effective field theory. I call it M reference for the mass term minus lambda reference over 4 factorial L to the 4 minus C1 reference L to the 6. And from some other exercise we know that this Lagrangian is sufficient. It contains the fully general terms which are necessary to describe physics at the dimension 6 level of this theory. So there are 3 physical parameters: the mass, the quartic coupling, and the 6th order coupling. Let us contrast this with the general Lagrangian, and maybe let me give you the result immediately. So the general Lagrangian contains here a free coefficient in the kinetic term. So the kinetic term is not canonically normalized, but it has an arbitrary prefactor A1. Then the mass term, I redefined it compared to the exercise sheet. So I call it A1 times M tilde. However you call it, the mass term has an arbitrary coefficient. Then there is some lambda without index times L to the 4. And there are 3 dimension 6 operators, namely minus C1 times L to the 6 minus C2 times L cube D'Alembert L minus C3 L D'Alembert square L. So here we have the squared D'Alembert operator, in other words, a 4th derivative. And here has gone into an analysis that we did in the exercise, namely the most general basis of dimension 6 operators up to total derivatives. Contains the 3 operators L to the 6, L cube D'Alembert L, and L D'Alembert square L. And we did the analysis in the exercise, so let me not repeat it here. So in our general ansatz for the Lagrangian, we have 6 free parameters. In the specific one, we have 3 parameters. And the outcome of the analysis will be that the physics described by both is the same. That means 3 out of the 6 parameters are actually redundant. They do not influence physical observables. They only influence unphysical quantities such as green functions, expectation values of the field operators, but not physical quantities. Let me specify the Feynman rules. The Feynman rules, first of all, are for the propagator of the theory. The propagator of the theory in the reference case, so the simple case is simply I divided by p square minus m reference square, the usual propagator Feynman rule. But in this general theory, we have the additional normalization A1 in front of the kinetic term. And as you hopefully know, the simple rule for the propagator is that it is simply the inverse of the kinetic term in the, or of the differential operator of the bilinear term in the Lagrangian in momentum space. So here we get I divided by A1 times p square minus m tilde square. So the A1 coefficient goes into the denominator. Okay, let us simply go on. The next Feynman rule is for the quartic interaction, and in the reference theory it is simply minus I lambda reference. But in the general theory it is different. First of all, we have the L to the 4 term over there, but and that gives minus I times lambda without index. But then we have the C2 term. The C2 term also contributes to this Feynman rule, and it involves a derivative. The derivative gets converted in, so D'Alembert gets converted into minus p square of the incoming momenta. And according to symmetry, we need to sum over all the 4 minus p squareds for the 4 incoming momenta. And due to symmetry, we also get 3 factorial. So we get times 3 factorial times C2 times the sum of I goes to from 1 to 4 pi square and plus times the usual factor I for each Feynman rule. So here there is a plus. Okay, so the Feynman diagram is much more complicated, and it is now momentum dependent, whereas in the reference theory it is momentum independent. Then we have the vertex with 6 external legs. In the first theory, this is simply minus I times 6 factorial C1 reference. In the other case, it is minus I 6 factorial times C1 without an index. That is equally simple. And then we have the term with C3. The term with C3 gives us a Feynman rule. In the exercise, you almost didn't believe it, but it is a Feynman rule with just 2 external legs. And just to make it look different, let me use a square here to denote this C3 Feynman rule. It is a bilinear vertex with 2 external lines and some incoming momentum p. And the Feynman rule, according to the usual rule, D'Alembert gives minus p square, D'Alembert square gives plus p to the 4th power, and we have a symmetry factor, so we simply get minus 2 times I C3 p to the 4th power. So and this applies only to the general case, so in the other it is 0, and here we have minus 2 I C3 p to the 4th power. Okay, now this describes the 2 versions of the theory, the simplest one and the most general one. with either 3 or 6 free parameters. And here the Feynman rules are obviously excessively complicated. And now let me explain to you how we can calculate physical observables from both theories. And obviously the result is going to be the same. The calculation here is way more complicated. And so in principle it would not be necessary to do it, but that should come out as a result and as a lesson of the exercise, because I want you to note that there is this redundancy, and later on, since you will then know that the redundancy exists, you have the opportunity to simplify your theory before doing calculations. You would then in practice see this Lagrangian and remember, oops, there was this opportunity to simplify the Lagrangian in a certain way, which we are now learning. And therefore, before using those Feynman rules, you apply equations of motion, and you go here and then do the calculation of the observables. That is exactly the point. But the second reason why I want you to follow me a little bit and look at the details of the calculation is that if you have loop calculations, then the loop calculations will lead to expressions which have all these properties. So loop calculations involve, for example, so-called self-energies. They can behave like this. Loop calculations involve corrections to such a vertex, and the loop corrections will have such a behavior, even though it is just even more complicated than this, of course. So if you understand how to compute observables from this theory, you will also understand a few important lessons how to extract observables from a loop calculation. Because these details that we are now going to see regarding LSC reduction and extracting S-matrix elements and so on, they have to be repeated for loop calculations as well. So therefore, this has multiple reasons for being useful. And so let us now embark on the computation of observables. So, for the observables, the first thing is you need So, for the observables, the first thing is you need the full propagator. Including loops or including higher order corrections. And then it is often not called propagator, but the two-point function. We need the two-point function. And what is the full propagator, including higher order corrections or including corrections at all here? So this is the three-level propagator Feynman rule, but this is not the only Feynman diagram we need to consider for a two-point function. Why not? Because of this vertex here. So this now contributes, and so there is a Feynman diagram that looks like this. Okay, and we simply need to add the Feynman diagrams. There is a third diagram that looks like that. And so on. The number of Feynman diagrams which contribute is infinite. Infinitely many three-level diagrams. And the character of the diagrams is such that this is a geometric series. So here we have one propagator, and here we always have the same propagator and then multiply it with this block, then with a block squared, with a block cubed, and so on. So we literally get a geometric series. And in the notes you can see it in more details, and the result is simply this structure, the original propagator, a1p square minus a1 m tilde square, and then the Feynman rule here goes into the denominator, minus 2c3 p to the fourth. So we have this structure in our propagator. Now, what is the physical meaning of such a propagator? And I'm not sure whether you did this in QFT1 lectures. We did it a few times, but not always. But let me now drop the result. So the first important physical meaning of this propagator is the physical mass. The physical mass of a particle is the eigenvalue of the p-square operator, and the eigenvalue of the p-square operator corresponds to the location of the pole of this two-point function. So this two-point function has a denominator. The denominator can go to 0. That corresponds to a pole in the variable p-square, and the location of the pole is always equal to the physical mass of the particle described by the theory. So let's give it a name, m physical square. And if you work out what that is, the pole is not at the variable m tilde. So m tilde is not the physical mass. M tilde is the mass parameter of the Lagrangian, but you will see here that the mass parameter of the Lagrangian does not need to coincide with the physical mass described by the overall theory because of interactions. And so the physical mass is not equal to m square, but it is given by m square plus a correction, namely plus 2c3 over a1 times m tilde to the fourth power. That is the location of the pole in the variable p square. You can check it, and therefore this is the physical mass. A keyword that you can look up for this relationship is the so-called Tellin-Lehmann representation. So, for example, we did all of that in our quantum field theory lecture 2019, which is on YouTube. But of course, this is standard. And in the reference theory, what is the pole in the reference theory? In the reference theory, this is just m reference. So, because there is no interaction there. So, that would be equal to m reference square. And if we want to say that there is any chance that the theories describe the same physics, then the first thing which must be equal is the physical mass of the particle. And therefore, we must identify m reference square with this expression. We cannot identify m reference square with m tilde square, but with this polynomial. Otherwise, the physics is going to be different. Then the next important thing from the propagator is the residue. The pole corresponds to the physical mass, and at the location of the pole, the propagator now has some residue, forgetting about the I. And the residue is obviously non-trivial. So let's calculate the residue at the pole. And the name of this is curly Z, curly capital Z, and it turns out to be 1 over A1 minus 4C3 m tilde square. And of course, in the reference case, the residue is simply 1. So you will see in a second why we need the residue. But so much for the propagator. B, let us calculate further observables. Let us calculate first a scattering with 4 light particles. And according to the LSC reduction formalism, there is a recipe how to compute a physical S-matrix element or scattering amplitude or the so-called T-matrix element for this process. Namely, you have the following recipe. You calculate the amputated green function with 4 external legs. So these are basically the Feynman diagrams for the process here at tree level. But after you calculate the Feynman diagrams without external lines, so the external lines are dropped, that is the meaning of amputated. But after amputating it, you multiply with this square root of z for each external line as a normalization. That makes the normalization physical. Otherwise, the normalization is undefined, and you cannot interpret this as a physical scattering amplitude, but this provides the correct normalization factor, and that is why we calculated the residue of the pole before. And why we need that, that is the proof of the LSE reduction theorem for the S matrix. So here, in this case, what are the Feynman diagrams for the 2-to-2 process? How many Feynman diagrams are there for 2-to-2 scattering? Yes, so in this list it would be just one Feynman rule because we have combined it. But indeed, so there is only this Feynman diagram. And the external legs are not part of the diagram, so the diagram is literally given by the factor that we see in the list over there. And then we multiply with this. So therefore, in the reference theory, this is equal simply to minus I lambda reference, okay? Because that is the Feynman rule and the Z is 1. Therefore, that is the result for the physical scattering matrix element. As simple as that. However, in the general theory, it now becomes ugly. So in the general theory, first of all, we have a momentum dependence in the vertex. But the momentum dependence actually simplifies because the p square of all the external lines are now equal. So pi square, they are set equal to what? They are set equal to the mass of the particle, but which mass? The physical mass. Because the physical particles which appear in the scattering, they have momentum which is equal to the physical mass, and that is why we needed to compute the physical mass. So we will plug that result for the physical mass into the pi square in the Feynman rule over there. Then we have an expression for the diagram which contains over there 4 times the physical mass square. Then we multiply with the second power of this. We expand up to first order in the coefficients C, and we obtain the following expression. Minus I lambda divided by A1 square minus 8I lambda C3 m tilde square divided by A1 cube plus 24I C2 m tilde square divided by A1 square. Okay, so after some ugly calculation, this is what you get. 3 terms which depend on the coefficients C3 and C2 and also on the m tilde square, the mass parameter, but not the physical mass. Okay, so likewise, let's go to the even more complicated case, namely 6-particle scattering. And again, our physical S matrix element is given by the amputated green functions, which look like this. So all Feynman diagrams with this shape, but without external line corrections, multiplied with square root of z for each external line, so square root of z to the 6th power. Now, how many and which Feynman diagrams are there? So, which Feynman diagrams contribute to this process? There is now more than one, but the first one is simply the direct C1 Feynman rule with 6 particles. So this vertex appears, but of course it is not the only one. So we can do something with a quartic vertex and then we get Feynman diagrams with this typical shape. Okay. So we get this. And we might even also consider such a Feynman diagram. And then we need to plug in all the Feynman rules. Again, we set in the general theory the external momenta to the physical mass and multiply with the square root of z, and you can find the calculation in the notes. Let me just give you the result. So in the reference theory, we get equal to minus I lambda reference times the sum over 10 different index combinations of the indices ijk times 1 over pijk square minus the reference mass squared minus 6 factorial times I times C1 reference. Okay. So here this comes obviously from the 6-point vertex, and this comes from the diagram with the 2 lambda vertices, and here there is a square. And we have done similar calculations in the exercise. Now let me give you the result for the calculation in the general theory, where we have here a more complicated Feynman rule. Here the Feynman rule becomes momentum dependent, of course. And here we then have 3 external momenta, which we set equal to the physical mass square, and 1 internal momentum, which is this pijk square. So then we get terms where the pijk square is also in the numerator. Then we can make some manipulations and cancel the numerator pijk square and get some additional terms. We also have to calculate this, multiply with the square root of z, and after some calculation we obtain the following result, namely sum long bracket times the same sum over ijk of 1 divided by pijk square minus the physical mass square. So in the calculation I deliberately replace everywhere the m tilde by the physical mass, such that the denominator structure here becomes equal. And in the curly bracket we have the following: minus I lambda square divided by a1 to the 4th power minus I lambda square c3 m tilde square divided by a1 to the 5th power times 16 plus I lambda c2 m tilde square divided by a1 to the 4th power times the prefactor 48. So this is the resulting prefactor in the general theory, and then we also have such a constant term without momentum dependence, which has the following form: minus I times C1 times 6 factorial divided by A1 cube plus lambda cube C3 divided by A1 to the 5th power times the prefactor 20 minus lambda C2 divided by A1 to the 4th power times the prefactor 120. Small fun comment: I struggled for a few hours with these prefactors here until I discovered that the original prefactors that I had for some time had to be multiplied with a factor 10 because they appear in the sum over 10 equal terms. Okay, and then everything worked out smoothly. Okay, very good. But that is the result. And so now the moral of the story is that all the observables that we consider the physical mass, the physical scattering processes with arbitrary external momenta. So these are infinitely many observables. It's not 3 observables, it's infinitely many observables because the momenta are all arbitrary, angles and so on. They can be the same regardless what you choose for the 6 parameters in the general theory. You can always find values for the 3 reference parameters such that the reference theory produces the same physical result. Therefore, the theory in truth has not 6 free parameters but only 3. So as a simple observation, for example, lambda always appears in this combination, lambda over A1 square. C3 always appears in this combination, C3 over A1. C2 similarly always appears in this combination, C2 over A1 square. So the parameters do not appear in arbitrary combinations but only in specific combinations, and that is how you see that some combinations of them are actually redundant and are not important to describe physics. So to sum it up, the result is if the reference theory parameters are chosen as the following, namely m reference square is equal to m tilde square plus 2c3 over a1 m tilde to the 4th, then the physical mass is equal. And similarly, lambda reference and C1 reference is equal to some particular combination which you find in my notes and which you can obviously see. So here you see the equality that you need for lambda. That must become lambda reference and something similar. So here the curly bracket must become C1 reference. Then all observables are equal. So there are redundant parameters in our general theory. And we have learned that the hard way by doing the explicit computation. But I remind you that doing the hard way is necessary if you have loops. Where, for example, this curly z, the residue of the propagator is not equal to 1, then you need to do exactly that. If you have loop corrections to the propagator, which look like the square, that the square could become a loop, and then, of course, you need to calculate such loops and take them into account, and the calculation of them would be similar, have a similar effect. Let us continue with a discussion of field transformations, which was the third or final part of the exercise. We will now analyze basically the most general set of field transformations that we can apply onto our Lagrangian without changing the physics, and calculate the impact how the Lagrangian changes as a result of the field transformations. Then we know that we get family of physically equivalent Lagrangians, and we will see that one of them is such that you can transform the general Lagrangian directly into the reference Lagrangian. In other words, you can use the field transformations simply to eliminate 3 out of the 6 parameters. And that is what you would ultimately do in practice, of course, if you want to simplify your theory as much as possible. So in the general Lagrangian, which is a functional of L, we apply the following field transformation. The field L becomes the most general polynomial of 3rd order, or in other words, the most general nonlinear expression which is compatible with a discrete symmetry and which involves or which generates terms up to dimension 6 in the Lagrangian. Everything else is unnecessary for us. So the most general structure of that kind would be a linear term with an arbitrary coefficient plus a term B1 times a dimension 3 operator, which has the same symmetry property, is linear, namely D'Alembert L prime plus B2 times L prime cube. So these are the three only expressions of up to dimension 3 which have the same discrete symmetry property as the original L, and for simplicity drop the prime. So we will not distinguish anymore L prime and L. So this gives effectively, this simply changes the coefficients in this L general. So the L general was already the most general Lagrangian that contains all possible operators up to dimension 6. If we apply this most general field transformation, nothing new can appear. There are no new structures. All the structures which appear have already been there before, so only the coefficients change. Therefore, we can write the changes as following, namely C2, actually let me not write down the general thing, but let me draw one more conclusion. So we can then show, using the result that we had before, the explicit calculation of the observables, that the observables remain equal. So in other words, that can be explicitly verified. Therefore, we can use the field transformation to simplify the Lagrangian. Can use field transformations to simplify L general without changing physics. Okay, so once we know that the field transformations do not change physics, we can use them to simplify the Lagrangian. And one way we can do is we can apply field transformations. So using now the result of how the coefficients change in terms of this, we can make it such that C3 changes to 0. So from ever C3 was before, we now calculate square root z b1, b2 such that after the field transformation C3 becomes 0. Similarly, we can do it such that C2 after applying this becomes 0. Similarly, we can do it such that the coefficient A1, this kinetic term coefficient, becomes simply equal to 1. We can do all that, and if we require these three conditions, then those coefficients z, b1, b2, they are fixed. So you will look at the explicit expression for how C3 changes, then this condition gives you some equation how to determine these three quantities. Second equation, third equation. So from the three equations, you know exactly how the three coefficients in the field transformation have to look like. Okay, so then the field transformation is fixed. Since it is fixed, you can then plug in the fixed transformation into the other coefficients, C1, A1 m tilde, or m tilde square, and lambda. So they also change, and they change in a way which is now calculable, and let me just copy how they change, and you can see the calculation in the notes. C1 becomes C1 over A1 cube plus lambda C3, lambda square C3 over A1 to the 5th power times 1 over 36 minus lambda C2 over A1 to the fourth power times 1 over 6. Similarly, m tilde square becomes m tilde square plus 2 m tilde to the fourth power times C3 over A1. And lambda changes to lambda divided by A1 square plus lambda C3 m tilde square divided by A1 cube times the prefactor 8 minus C2 m tilde square divided by A1 square times the prefactor 24. So this is the outcome. You now know that you do not change the physics if you change the 6 coefficients in this way according to the field transformation. And lo and behold, you observe something beautiful, namely this change is exactly the same as that change over here. Namely, so looking at the simplest, m tilde square becomes exactly this polynomial. That is exactly the same as the relationship to this reference mass square. And similarly, for lambda and C1, it is exactly the same, including these strange coefficients 20 and 120. That comes because you need to divide them by 6 factorial. 6 factorial is 720, and therefore 120 divided by 6 factorial is 1 over 6. 20 divided by 6 factorial is 1 over 36, and that explains these coefficients here. So, the summary of the discussion is the general theory becomes the reference theory, the parameter relations are as in our calculation 2 here. This ends the discussion of our exercise number 4. So you see again that we have studied the ambiguity of the Lagrangian of the EFT in 2 different ways. We worked through the hard way of calculating all the observables using the general Feynman rules with momentum-dependent vertices and a strange propagator. But it worked out, and we obtained that the reference theory describes the same physics if we have certain parameter identifications. Then we applied field transformations, which do not change the physics, and we see that using them we can immediately transform the general Lagrangian into the one of the reference theory by applying specific coefficients in the field transformations. So again, everything works out beautifully, and we have 2 different ways of analyzing the same thing, namely this ambiguity. And so from now on, you have this explicit experience, and you know that such field equations or field transformations can be used to simplify the Lagrangian of the EFT. And just to make sure once again, physics doesn't change, S matrix do not change, and the physical masses do not change, but what changes are arbitrary Feynman diagrams for off-shell green functions with arbitrary off-shell momenta. Those are not directly physical observables, but the actual physical S matrix elements, they remain the same. Any questions? Yep.
I have 2 questions. The first one would be, so a specific one, so in practice we will always have a Lagrangian which have some constraint or some symmetry, so that I find the field transformation that happens, the most general field transformation that happens to be according to this symmetry
Yep.
of the Lagrangian. And can this discussion be, because normally we say for the fundamental theories, not for the EFTs, that we find the easiest Lagrangian, which is Lorentz invariant and which is gauge invariant. Can this discussion can that be explained explain in the same ways as here why we find the easiest one, and that should be the one which is explained later?
I'm not sure I fully understand what you have in mind. Gauge invariance doesn't play a role here, but gauge invariance could be studied in a similar way. Of course, it is a little bit more involved. And for example, we might wonder whether the Lagrangian of an EFT is also gauge invariant, or whether it has non-gauge invariant vertices and terms in the Lagrangian, and we will come to that. But on the other hand, yes, it is important that we are able to simplify the Lagrangian in order to exhibit really the physical essence of the theory. However, it is also sometimes really interesting to study those more general Lagrangians, because you might be actually interested in describing not only the same physics as your fundamental theory, but you might want to actually describe the same off-shell green functions as well. Sometimes that is also necessary, and then you must work with this more general Lagrangian. So there are applications of both approaches. Whether this fully answers the question. So are there other questions or further discussions? Yeah. So these are the 4 lessons, or 2 times 2 lessons that we drew from the previous discussions from the previous weeks. Effective field theories seem to exist, and they are ambiguous. So let us now go on with the lecture. Let us discuss reasons and explanations. So I deliberately gave you lots of calculational examples to give you practice and to have you make your own observations. And we have seen the lessons. Effective field theories can exist and can describe the same physics and the same results of Feynman diagrams as full theories. But I have not yet given you the general proof why that is the case. We have just observed it in several examples. Similarly, we have now clearly stated that field transformations can be applied to the Lagrangian without changing the physics. We have observed it to be true. But why is this actually the case? That we have also not discussed. And so let me now explain both, to give you a general argument why these effective field theories exist and why they have the form that we have observed in our explicit calculations. And in order to do that, we work with a path integral. So for the path integral, we can represent green functions which correspond to arbitrary Feynman diagrams using the path integral. So this would be a green function, time-ordered product of some field operators. The path integral expression for this is a path integral over all field configurations of the theory. So we have light fields and heavy fields. So we integrate over all field configurations of both. Then we have here the classical counterpart of those operators, times e to the I times the action. So in the full theory, we have a path integral where we have an exponential with I times the full action, the space-time integral, over the full Lagrangian of the full theory. And the full Lagrangian, of course, depends on the light and the heavy field. That is our path integral expression. And now comes the explanation why the effective field theory exists. And at the same time, why do we call it integrating out a heavy particle? Because that's exactly what we will now do. We simply carry out the integration over the heavy field, that's all. So we carry out this integration. And so if we then simply go on with our calculation, what happens is the following. We get, as a result, a path integral only over the light fields. Then these L functions, they do not change by the integration over the heavy field, so these factors just remain here. And then what we get is the result of the integral over the heavy field of just the exponential of e to the I times the action, including h. We integrate over h. And what is the result? The result is simply some functional of the light field. It cannot depend anymore on the heavy field, but it must, of course, depend on the light field, since this depends on both. So let us just give it a name. And the name I will give it is W subscript H of L. So let's call the result, by definition, e to the I times WH of L.
طبعا من هنا نقول أنه يعني الباث انتجرال الذي يكون من أجل إخراج المجالات الثقيلة من المعادلة. في كتابي كما لاحظتم في الحلقة السابقة أن تعبر عن B ال H اللي هو كتلة ال H اللي هو ال heavy field اللي هي المجال الثقيل، تعبر عن B تعتبر ماذا؟ B تعتبر معامل أينشتاين للامتصاص المستحث، والتي تساوي معامل أينشتاين للانبعاث المستحث. فهو يخلص من B حتى يجعل فقط A هو معامل أينشتاين للانبعاث التلقائي. وهذا يتفق مع ما توصلت إليه، لأنه معامل أينشتاين للانبعاث التلقائي يرتبط بماذا؟ يرتبط بالكتلة بالجاذبية، أو يرتبط بما تفعله الكتلة في الفضاء ثنائي الأبعاد، أو تعالوا نقول أنه يرتبط بماذا؟ يرتبط ب قدرة الفضاء ثنائي الأبعاد على طرد الكتل. قدرة الفضاء ثنائي الأبعاد على طرد الكتل. لو تتذكرون 10 أس ناقص 95 10 أس ناقص 95 هذه تعبر عن مدى صعوبة الفضاء الثنائي لطرد الكتل. طيب ما الذي يسهل هذا الرقم وما الذي يضخم هذا الرقم؟ هو الكتلة موجودة في البسط اللي هو M أس 4 على R تكعيب. هذه النسبة هي تجعل 10 أس ناقص 95 هذا الرقم الكبير ينقص إلى أن يصل 1. طبعا إذا وصل 1 هذا يعني أن الفضاء ثنائي الأبعاد سيضخم مباشرة، سيفعل آلياته في طرد الكتل. فهنا ما حدث هنا أنه تجاهل 10 أس ناقص 95 فقط ليحسب اللايت فيلد اللي هو L لايت فيلد. واللايت فيلد هنا في الانتجريشن أو في الباث انتجرال نعبر عنها بالبي اللي هو بكمية التحرك. كمية التحرك عبارة عن طاقة. وفي معادلتي أو في نظريتي أو في كتاب الحلقة 53 عبرنا بها البي، عبرنا بها بكثافة الطاقة الموجودة في وحدة الحجم حتى يفعل الفضاء ثنائي الأبعاد الدفاع النفسي. فهناك تشابه، لكن هو عمل integration out of H اللي هو الهيفي فيلد. وبالتالي في نظريتي سنعمل على تجاهل البي. طيب إذا تجاهلنا البي ماذا نتحصل؟ نتحصل على كتل لها شكل محدد ولها كميات محددة. هذا هو ما يربط نظريتي ب الافكتيف فيلد ثيوري. لكن أنا بالنسبة لي أنا لا أريد أن أجد أن ألاحظ فقط النتائج، لا، أنا أريد أن أدرس النتائج وبالتالي أنا بالنسبة لي B مهمة، كما أن في هذه النظرية أن H ستكون مهمة، أيضا أنا بالنسبة لي B هي المهمة. فبي معاملات أينشتاين هي مهمة بالنسبة لي، لأنه هي التي تحدد شكل الكتل وكمية وشكل الكتل وكميتها. يعني احنا نعلم أن الإلكترون لديه كمية معينة من الكتلة ولديه شكل معين من الكتلة، ولديه السبين. السبين يلعب دور كبير طبعا، السبين يلعب دور كبير جدا، وحتى الآن أنا أريد أن أعرف كيف يلعب، لكن السبين يلعب دور كبير جدا جدا، والسبين تعتبر آلية من آليات الفضاء صناعة الأبعاد في الدفاع النفسي. الشحنة أيضا تلعب دور، الشحنة تساهم مع الكتلة طبعا، تساهم مع الكتلة في أنه تسبب تهديد للفضاء صناعة الأبعاد غير متناظر، لكن كميتها أو تأثيرها هو قليل جدا، لكن التأثير الأقوى هو من الكتلة، لأن كتلة الإلكترون بالرغم من صغرها حسب موقعنا نحن، لكن إذا تقدمنا ووصلنا إلى أبعاد الإلكترون سنجدها كتلة ضخمة، وبالتالي الكتلة تلعب دور أكبر من الشحنة. الشحنة أيضا تتضخم لكن ليست لهذه الدرجة. فما يفعله هو الانتجريشن اوت اوف هيفي فيلد، سنكون نحن في حاجة له، لكن متى سنكون في حاجة له؟ عندما نريد أن ندرس شكل الكتل، وندرس لماذا كتلة البروتون ثابتة، لماذا كتلة الإلكترون ثابتة، لماذا كتلة الميون ثابتة، وأيضا ربما تخبرنا هذه الآلية بكتلة الفوتون، تخبرنا بكتلة الفوتون. عموما سنحاول نكمل قبل صلاة العصر إن شاء الله. طيب تبقى لنا جميل. طيب تعال نكمل.
And this WH of L is some functional of L, but not of capital H. And this corresponds to the jargon that we have integrated out the heavy field H. So as simple as that. In that sense, we have already proven that an effective field theory exists, and the action of the effective field theory is simply this WH. However, what we have not yet established is that this action, WH of L, whether it has the form of a normal action that we know in quantum field theory, namely an integral over a Lagrangian density, where the Lagrangian density is actually local. Not every functional is a space-time integral over a local Lagrangian density. And second, and more in detail, we have observed that we can obtain the action by using the equation of motion trick. And therefore, let us prove now why the equation of motion trick works in getting this WH of L. And that is specific to tree level. So at tree level means we work at a classical limit. So at tree level means we work at a classical limit because loops are of the order h bar. Therefore, if we neglect loops, it means we neglect corrections of the order h bar, and that means we work at a classical limit. So if we work at a classical limit, we have to evaluate the path integral in the classical limit, and we know what that means. Namely, then in the path integral, not every path contributes, but only the classical path contributes, which corresponds to the stationary point in other words, to the solution of the equation of motion. So only the classical path contributes in this dH integral. And therefore, we immediately obtain the result WH of L. So is obtained by the integration over all field configurations, and the classical limit means that the integral collapses to one term, namely to the term where here we replace the H by its stationary point, by its solution to the equation of motion. So we get, this is the full action where we replace H by its solution to its classical equation of motion. And that explains the existence of the EFT and the equation of motion procedure.
طبعا الكلام ده بغاية الأهمية، لأنه ال EFT تعمل على الكلاسيكال ليميت، وأنا ذكرته طبعا في الفرضيات، آليات الفضاء، فرضيات نظرية عريس وآليات الفضاء الثنائي الأبعاد الدفاع النفسي، أنه داخل الفضاء الثنائي الأبعاد فإننا نحتكم إلى الكلاسيكال فيزيكس، وليس يعني صراعات داخل الفضاء ثنائي الأبعاد هي صراعات بطيئة. بالتالي ما دام نحن نتكلم عن تفاعلات في الجسيمات الأولية فإننا نتكلم عن فيزياء كلاسيكية، لكن نحن من وضعنا نحن كملاحظين نراها فيزياء كمية وتنطبق عليها خواص الفيزياء الكمية من الكوانتيزيشن، من الانسرتينتي، من الفايمان دياجرامز، من يعني في معادلة ديراك، السرعات العالية، كل ذلك هي خواص كمية تنطبق بالنسبة لأننا نحن موجودون في موقعنا وننظر إلى الأبعاد الصغيرة. الأبعاد الصغيرة تتميز بماذا؟ تتميز بمعدلات تدفق زمكان عالية، وهذه هي الفيزياء الكمية. ميكانيكا الكم هي إلى معدلات تدفق زمكان وملاحظين فقط.
So that is compatible with all our explicit calculations, but now you see the general reason why it will work in all cases and why what we have done is generally correct. Any questions? So it is really as simple as this. However, we will have to come back to similar discussions when we work at the loop level, because obviously we have made here the classical approximation. And if we work at the loop level, these steps here are of course different. And also we will then have to be a little bit more careful here about integrating just over H and doing nothing to the L integral. So we will have another look at the whole discussion here. But for the tree-level situation, it is correct and it is in agreement with our explicit computations. So therefore, take this as a kind of preliminary or first sketch of the way to look at this whole procedure, and we will do similar discussions with a higher level of fine details later on. So, okay. We can do similar discussions for the ambiguities. We have only 5 minutes of time, so do you have more questions? Otherwise, I would start saying a few words on the ambiguities from a similar perspective. No questions? Okay, then let me continue. So about the ambiguities. Looking at the path integral, clearly the physics cannot depend on the variable choice in the path integral. Therefore, the physics and observables cannot change under path integral variable substitutions. And again, this statement is a little bit sketchy, but let's for now work on this sketchy path. In the path integral, clearly the physics cannot depend on the variable choice in the path integral. Therefore, the physics and observables cannot change under path integral variable substitutions. And again, this statement is a little bit sketchy, but let's for now work on this sketchy level. So if we do variable L goes to L plus a small variation, so let's call it delta L, and then this would be some functional, like we just had in the case with B1 plus B2, where we had here D'Alembert L and L cube, and something like this. Then the path integral measure dl is invariant. So, and let's do a footnote of this later on. But the path integral measure is invariant under such a substitution. And second, the action, the Lagrangian over some field, changes into Lagrangian of L plus delta L, which you can write as the Lagrangian of the original L plus some variation of the Lagrangian. So this field transformation generates additional small terms of order of this variation delta L, which is assumed to be small as well, in the Lagrangian. So therefore, if we look at the path integral before and after the field transformation, the measure is the same and the Lagrangian changes by delta L. So it simply means the original path integral with the original Lagrangian and the modified path integral with the additional delta L describe the same physics. And therefore it basically means you can change the Lagrangian from the original L to this L plus delta L. Physics will stay the same, and the delta L is obtained by applying such a field transformation onto the original Lagrangian. So let's write this down. L and L plus delta L describe the same physics, and this obviously explains our observations on redundancy, which was this exercise 2.4, the second part that we discussed before, and the equality to field transformations which was the exercise 2.4, the third part. Okay, so again, a very simple observation in the path integral immediately shows you why these field transformations can be applied and why they do not change the physics, since they simply correspond to a variable substitution in the path integral. As simple as that. So let me make the footnote explicit and then we stop, and next time we will start with a summary of the whole section and then we begin with section 2 of the lecture. So just a note on this footnote here. This fact that the path integral measure is invariant is an exact statement in including loops in dimensional regularization. Where it has a special name, namely regularized quantum action principle. And as a reference, we have proved this in 2 different lectures, so I just refer to them. So see, there was a multi-loop lecture, or the quantum field theory 2 lecture, section 186. So there we made exactly this statement and proved it explicitly. So it's an all-order statement valid in a specific scheme, namely the dimensional regularization scheme, which we will mostly use. And therefore, this part is not a sketch, it is exactly true, and so we can use that to establish the validity of these field equivalences. All right, so much for that. Then let us continue on Thursday with a small summary of our section 1 and then continue with section 2 of the lecture. So see you then.
جميل. ربما نكون يعني أنا أكون لا بخرج بشيء كثير من هذه المحاضرة، لكنكم ربما تخرجون بشيء كثير، يعني الأفهام تختلف، يعني غير كذا. يعني أنا في بيئة فيها ملهيات كثيرة جدا، ناهيك عن أنني يعني لم أدرس أو لم أتعمق في معادلات فايمان. يعني مفترض أن أدرس QFT1 وQFT2 إن شاء الله، سأمر عليها إن شاء الله يعني من خلال هذه السلسلة القادمة أو بعديها، الله أعلم. لكن من الأهمية بمكان، يعني معادلات فايمان ولماذا حصلت الكونتراكشنز، وذكر شيء يسمى LEZ كونتراكشن، نظرية اسمها LEZ LBZ، مفترض أن ندرسها جيدا. ربما أكون مررت عليها في تسلسل التاريخي، لكن في النهاية التسلسل التاريخي يتحدث عن كتاب، فأنا أريد محاضرات، هذا هو الفرق. فأنا أريد محاضرات تتحدث صراحة عن هذه الآليات، وسأدرسها إن شاء الله في مقتبل الأيام بإذن الله تعالى. جميل، هكذا نكون انتهينا من الحلقة الثالثة، وسنتحرك إن شاء الله في الحلقة الرابعة.